As with many things in C++, the standard template library doesn't really make a whole lot of sense until you actually start using it. So when you hear about the standard library, you think STD. But when somebody mentions STL, you're like, wait, what is that? And they'll tell you it's the standard template library. Often confused with the standard library. They're two very different things. So the standard template library is a software library for C++, and it's influenced by the standard library. So they are two very different things, even though they usually come packaged together nice and neat. It provides four common components called algorithms, which is, a set of algorithms or programming logic that you can use, containers, which basically hold data, functions, which of course are exactly what we're talking about. The difference here is that you can make these things templates, and you also have iterators, which doesn't make a whole lot of sense until you really learn the rest of these here. But at its core, let's say you have a task like clean the house. I clean the house, you clean your house, somebody else cleans their house. You could turn that into a template, a generic standard way of doing things. Notice I said the word generic. Templates and generics are often used, interchangeably, and they're not the same thing. So C++ has templates where other languages have generics. So for example, C# and Java have generics, C++ has templates, but they do almost virtually the same thing. They allow you to throw different types of data into algorithms, containers, functions, and use iterators to go through them all. That gets really, really confusing. And you can feel free to read the rest of this here, but point being, until you actually see it in action, you don't really have that aha moment, and it gets very in-depth in terminology and technology. I like to actually show by example, so we're going to not really go into a lot of the theory here. So a lot of the standard template library actually makes zero sense until you see it in action. So just kind of recap here. The STL has algorithms. Those algorithms typically work on containers. Those containers hold data. Functions can also be templated. And you have iterators, which can iterate over the data in the containers. That's why it gets really, really confusing. So think algorithms, containers, and iterators all kind of go together, and functions, you can actually template those. So what are we really talking about here? Think of it this way. I clean my house, you clean your house or apartment, someone else cleans their dwelling, and so on and so on. Everybody cleans. If you can make a template so that everyone can clean regardless of who they are, your program's much more efficient. Let's go ahead and take a look here. So I have a function, I have a container, and I have some data types here. Let's say we want to make a function called add. An add is simply going to add two variables together. Okay, well, that's simple. I'm going to say add, and then we want to add an int and an int. So we can very easily take these guys and put them through this function, and it just works. Now, someone comes along and says, well, what about doubles? Well, doubles and ints aren't going to work well, so we have to, well, you guessed it, rewrite this specifically to take doubles. Okay, well, now I have two functions that do virtually the same thing. They're both going to add. And then somebody comes in and says, what if I want to add an int and a double? Crying out loud. Now I've got to go ahead and make yet another function. And this one is going to specify an int and a double. And then somebody else comes in and goes, well, what if I want to do a cat and a double, or a cat and a dog, or some infinite possibility? Really what we're getting at here is if you use simple logic and permutations, you see that you would have an infinite number of functions because you can have an infinite number of data types. This gets insane. This is where the standard template library really comes in and says, okay, we're going to turn that function into a template function. So instead of this insanity, we can get rid of all this and say, all right, we want to add a type to a type. And as long as those types are the same, like int and int or double and double, this will just work. We can just throw it at it. And the compiler figures out at compile time what to actually make here. The only real problem here is if you come in with like cat and double, then you've got to actually break this out and do something like this, where you would say, int or h&t or whatever letter you wanted, anything that represents two different data types. So that really fundamentally is what we're talking about when we say a function in the standard template library, or taking a function and converting it to a templated function using the standard template library. Now let's talk about containers, algorithms, and iterators. Basically, and I'm just going to, for the sake of space here, move these around. We're talking about a container. A container simply contains data. But again, we have the same problem we had with the function, where if we define, let's say, a list, and this list is going to hold ints, it will only hold ints. And you guessed it, if we try to take that same container and put a double in here, or a cat, it's simply not going to work because the data type doesn't line up. And then the compiler is going to freak out and bad things will happen. So instead, you, of course, have a templated container. So you would have a list of a certain type, and you could say, I want to hold integers, and then you could put all the ints in there. Or, of course, you could say doubles, and you could put all the doubles in there. This is extremely powerful and extremely cool. Now, when we flip back here, you're going to go, what about algorithms and iterators? So if you look at algorithms, they are, well, logic that operates on containers and sequences. So you can say, okay, I want to know some sort of value or I want to do some sort of operation on each one of these things. That would be the algorithms that are built into this. And you could say, well, I want to go through each one of these one at a time. So you would start at a position, and then you get this one, and then this one, and then this one, and you can move back and forth. It's actually extremely powerful compared to working with C++ without the standard template library. So in a nutshell, you can turn a function into a template function. You can have a container, which can have any infinite number of data types, and you can define that data type. And you can run algorithms over the information in the container, and you can iterate over each and every single item in the container. Wow, that is extremely powerful. Unfortunately, it's also extremely error prone, as we're going to demonstrate in the coming videos, especially when you add in the complexity that is Qt. So we're going to take a look at a template example. Why? Because templates are, well, extremely hard, and we need to understand them by working with them. Remember that templates are independent of a particular type, and this gets really super confusing in C++ land when you spend a lot of time learning data types. So let's make a function. And in this function, we're going to simply print something. Now comes the crux of the problem. What do we want to print? Well, we're going to print some type of value. All right, well, Now comes the hard part. What do I want to print? I want to print integers. But if I do that, that means I suddenly can't print doubles. So then I'd have to make another one called double, and then so on and so on and so on. Of course, you guessed it. The answer here is template. So we're going to say template, and I'm going to say type name T. So what we're doing here is we're making a templated function, and we now, instead of using a type, we can use this guy right here, our type name, which we have denoted as T. So now this could be an integer, a double, a string, whatever we wanted it to be. Let's go ahead and let's build this real quick, just to make sure that everything runs fine. This is a little bit different, so I wanted to step by step. You notice we got these brackets. If you skip that, you're going to have a hard time. So make sure it builds before you continue. Now we can go ahead and work with it. So I'm going to just say print. And we have to actually tell it now what we want to work with. So I'm going to work with an int. And let's give it the value of 1. Notice how now when we go to work with the function, we have to tell it, meaning we're saying print and use int. So under the hood, it's doing something like this. saying int. Let's grab this copy, and it's going to say bang and bang. So it's really replacing t with those. And we can just grab this and we can reuse it. And I'm going to do this a few times. So I'm going to say double. And let's say this is 126 point, I just need a number, 007. And then we want to use a Q string. And let's go ahead and make a Q string. Notice these are very different data types. An integer and a double are similar but very different because they're both numbers, but they're different types of numbers. And then a Q string is not even a number at all, but we can reuse this simple function because it is now templated. Go ahead, save and run and see this in action. And of course, 126,007, and hello. We get 0 data loss because we're not trusting C++ to try to cast that for us, so we're not losing that precision, and it works with multiple data types. This is extremely cool, but it has some complexity. You have to remember to use the template keyword and give it a type or a class, and use a letter, and then you have to use that letter throughout. In this example, we just have it right here as the parameter. And now you have to define it when you work with it. So under the hood, what's happening is you're calling the function. C++ is noticing the template and going, oh, I need to know what goes in these brackets. You give it what goes in those brackets, and then it converts it automatically, and you give it the information. Extremely powerful, but as we're going to see in coming videos, it's also very error prone. So let's take a look at template issues. Why? Because templates are very fragile and they can and often do fail. And when they fail in just amazing, disastrous consequences happen in your application, and you're often left struggling trying to figure out what's going on here. So a lot of instructors like to paint a rosy picture like these are perfect, and they are anything but. If you want bugs in your app, use templates. So I'm not going to try and dissuade you. They're very powerful and they have their place, but a lot of times you're going to have a lot of problems if you can't figure out what you're doing. Anyways, so we're going to make a templated function. We're going to start with the template keyword, and I'm going to say class T, class F. You may be going, now wait a minute. Didn't you use something different in the previous videos? Yes, I did. I used type name. Now, this is the other confusing bit. Keywords, type name, and class are used virtually interchangeably. There are some subtle differences, and you as the programmer will often not notice those differences. But at the very end of this, all the way at the end, here we go. There's one exception where you have to use class and not type name when declaring a template. For example, if you're going to use a class, that's why it's called class. So I almost always use class just because they are used virtually interchangeably. And if you're going to use a class, use class. Now, a lot of people, especially in the Q&A section, are going to fire off a lot of, no, you're wrong, this is what you should do instead. And in some cases, they're probably right. Again, based off the documentation and based off a lot of the majority of the answers out there, they're used virtually interchangeably. But I almost always use class. So a lot of people are going to say they're equivalent. A lot of people are going to say they're different. But at the end of the day, they both usually just work. All right, so let's go ahead and say we're going to return T using a function called add. And this is going to look just bananas, but bear with me here. Value 1, comma, and then data type of F, value 2. Notice I said data type of F. So what we're doing here is we're saying, hey, we're going to use two different data types, a T and an F, and they're both going to be classes of some kind. And we're going to make a function called add. It's going to return the value type of T, whatever we give it, but we're going to add T and F. That sounds really super confusing. And now you know why templates suck. I'm sorry, I'm just going to say it. Because it gets very confusing and you can break things very, very quickly. So return, and we're going to simply return value 1. And let's name this value 2, just so we can... Actually, let's name it value F and value T. Ah, super, super high tech here. So we're just simply adding two values and then returning it as t. Notice what we're not doing. We're not doing any type of casting. We're not even attempting to make sure that is a valid value of any way, shape, or form. But if we save and build, this will build, and you'll have zero warnings, zero problems, zero issues. It just thinks this is perfect. Oh boy. All right, so fasten your seatbelts here. This is what we're going to do. We're going to say qinfo, and let's go ahead and add. And we want to add an int. Let's see if I can get rid of those little yellow things. An int and a double. Now, because this is a template, we have to do it a special way. We need to tell it anything in the brackets. Remember, these brackets, we want replaced with whatever we type. So we want to tell it, I want an int and I want a double. So we have two different types here. T and F. So I'm going to say my T is an int, my F is a double. Now I can actually work with it. I'm going to say 1, and let's go ahead and add it to 4.6. All right. So what we're doing here is we are telling C++ what to do. We're explicitly casting this. We're saying explicitly cast it C++, do it for us. Which, of course, if we're telling C++ to do it, is an implicit cast, which gets very, very confusing. But when we run, yes, it's a 5. Or is it? Well, what's happened here is we're saying 1 plus 4.6. If you add those two together, it's really 5.6. But of course, we want it to return a t, in this case, the first one, which is an int. So it's going to implicitly cast it down to a 5 instead of a 5.6. That is super frustrating. You might not have wanted that answer. Okay, so that is a subtle bug right there. Now, let's take this guy. And let's change this. So I'm going to say, let's get rid of this. I don't like that. Let's just get rid of it. And I'm going to say 55 and true. Notice what we're not doing. We're not telling it what to do. This is bad. This is bad for a multitude of reasons because we are telling C++, hey, here's two values, just figure it out. And if we build this, drum roll, it builds. That is scary. And we can run this and we get 56. Wait, what? 56? We're saying 55 plus true. The computer equivalent of true is a 1, so it is converting that into a 56. Oh, that is super frustrating. Now, what happens if we grab this? Notice we're not telling it the data types, and we just simply flip those around. We're going to give it a true and a 55. What is it going to return? Well, we're telling the first data type is a bool, so it's going to return a true or a false. So now the order suddenly matters. It's returning true because it's not 0. Oh, that is scary. So the same data is going to give you two different results. And unfortunately, it gets way worse than that. Let's go ahead and do this. And we're going to say add 55 to true. Nope. Wait, what? What's going on here? Cannot initialize return object of int with an R value of const char point. So what's going on here is we are now telling the computer, hey, add this number to this character pointer. This is super confusing. Everything's worked, but now this doesn't work because we're trying to add two different types. And if we try to build it, okay, there you have it right here. Cannot initialize a return object type of int with an R value type of const char pointer. All right. Well, let's try the opposite here. Let's try, and I'm going to actually change that to my name so no one thinks that's a bool. Let's try this. See what it does. It actually builds, even though you really cannot add a string to an integer. Watch what happens. We get this thing right here. Where the heck did this even come from? Q byte array. What? Do you see the problem here? You're going to get some just radically unpredictable results if you get it working, and you really can't trust it. So, major takeaway from this is it is extremely powerful, but at the same time, you have to be very, very careful because you can get some just crazy information back from this, even though it compiles and it says there are no issues. So, buyer beware. Always, always, always declare your data types and make sure you understand what you're doing. Some of the complexities when it comes to templated classes is, well, you guessed it, Qt. So you can make a class and make a template, and we're going to show you what happens if you try to do a Qt object. So I'm going to right-click this project, add new, and let's call this class. Let's call this test. Make sure it is a Qt object, so it's going to include Qt object and add the Qt object macro in there. Next, finish. And let's just go ahead and add this into our project. Very simple, very easy. We just simply have our Qt object in here. Now we're going to turn this into a template class. So I'm going to use the template keyword. And this is a little bit misleading. I know this isn't going to work, and I know why, but unfortunately it takes a little bit of explanation. So we have template. We're going to say class with a T. Now we need a templated function. So I'm just going to say T add, and we're going to make this function use T and call this value1, comma, T value2. Let's just go ahead and implement this right here in the header. I'm going to return value1 plus value2 and add in our semicolon there. So nice, neat, all right on one line. Beautiful templated class. Everything looks like it's going to work until we go to build, and then, template class is not supported by Qt object. Oh, that is frustrating. So if you really examine this macro, you can just see they are blocking this. They will not allow you to use templates with Qt objects because it becomes an absolute train wreck to figure out what's going on. That is frustrating, but it is for a reason. Qt object is very complex, and you don't want to start playing around with it because, as we've seen, it can have disastrous consequences, and templates, by their very nature, are very fragile. And we want Qt objects to be very secure and very hard to break. So to fix this problem, it's actually ridiculously simple. You just simply don't use Qt object. That's right. So we can just strip this out. And we're just going to do a little bit of surgery here. We're going to strip out all the cute stuff in here and turn this into a normal C++ class. It's really not that hard. Now we just have a basic C++ class. I've still got this implementation file, so I can go into CMake list, go ahead and go in here, get rid of that. It's still out on the hard drive, so I'm going to flip over into the file system, and let's just go ahead and get rid of that. Going to remove, and let's flip back into our project and make sure that everything is beautiful and the way we want it. Now, if I go to give it a nice little build, it just builds perfectly. So yes, you can absolutely do this with C++ classes. The complexity comes in if you try to do it with a Qt object. You simply can't do it. Let's go ahead and work with this class here. So I'm going to say include, and we want test.h. Now I'm going to say test, and because this is a class, we have to give it the type. So we're going to call that int calc, and then Qt info. Notice how when I do this, the definition of that function now knows the type. So what it's done is it's gone in the background and it said, okay, so we're going to use this class, this templated class, give it this type, and now every time I use that type name, it's going to replace it in the code. That is extremely powerful and also, yes, as we stated before, very error prone. All right, so we can just do 1 and 4. And let's see that in action. 5, there we go. Very, very cool. And of course, we can just take this and use this with different data types. So I'm going to do this again, but I'm going to do this with a double. Let's call this decalc. And let's say this is 6.09, and let's do a 3.04, just because why not? And then we have 913. And this actually can do some pretty cool and unexpected things. So for example, we could, instead of our decalc there, let's grab this, and let's use QString. So we can work with a Qt class inside of a template, and let's call this scalc. And we're going to add in hello, and let's go ahead and make another one. Notice this just works. This is extremely cool. And it's converted it all into one QString hello world. That is extremely powerful. Major takeaway here is you cannot use QObject with templates. You have to have a C++ standard class, or it just simply won't work. And when you use it, you have to use the class and give it a type. From there, remember, anything in these brackets, it's going to go in and it's going to replace right here. And then anytime you see this type name, it's going to replace it with whatever data type you gave it. Okay, so templates and QObject. You can do it, it's just a little bit more challenging. We want to cover this because, well, objects cannot be copied. QObjects cannot be copied. We covered this, just kind of pound that into your head. Instead, we have to use pointers. Special note, Qt template classes are not inheriting QObject. For example, QList, which we touch on briefly in this course and really deep dive into in the intermediate and advanced course. Whenever you see a template class in Qt, it's not inheriting QObject. We have this very simple template function called display, which is going to take a class type T, and it's going to just QInfo it out. We can, from that, you guessed it, do a whole host of things very, very quickly. So I'm going to just say display, and we're going to display an int, and we're going to just display the number 4. And this just works. It's extremely powerful, extremely easy. Ta-da! And it works. All right, so I'm just going to very quickly whip through, and we're going to do some different data types here. So for example, let's go ahead and do a double. And let's call this 3.14. Let's go ahead and do a QString. Now you may be going, now wait a minute. I thought you said that QObjects cannot be copied. That's right, QString does not inherit QObject, which is why we can do something like this. Maybe if I could actually type it. There we go. Sometimes I get a little faster than I want to. So this all works. This works as expected. Now, I highly suspect QString is not inheriting QObject simply because we do want to be able to copy that at will. Now, watch what happens if I do something like this. So we're just going to make a QObject, and then we're going to go ahead and try to display it. Notice what happens right off the bat here. Invalid operands to binary expression QDebug and QObject called to deleted constructor. Yes, this is what we've talked about before. We cannot copy that object. So what we have to do instead is either pass a pointer or pass an address to it. And now notice how we have to do something here as well. Just tell it, hey, we're going to go ahead and use a pointer. Now, suddenly it works. There you go. QObject at that address. So major takeaway here is that templates are very powerful, very error prone. And if you're going to work with QObjects and templates, you have to remember, never try to copy the object. And QObjects themselves cannot be templated classes.